Hey there, students. Okay, here's the big kahuna. Let's take a look at how to give a formal proof for the definition of a limit applied to a specific problem. This is the epsilon delta definition being applied to prove that a limit is a particular value. So, just an overview here. There are 3 steps that I'm going to organize this in. 3 steps to prove, and this is with the epsilon delta, a limit. So step 1, and then of course I'm going to do each of these steps in an example, but just to write out what they are. Step 1 is to apply the problem specifics to the definition. And I'll show you what that means when I do it. Then step 2 is to write the goal of the problem, which will be determined by the definition. Write the goal, which is basically that the absolute value of f of x minus L is less than some epsilon, but this will be in specifics. And solve the inequality that gives us. Solve the inequality for the absolute value of x minus a. So then when it's solved for x minus a, then set the answer to be delta, which will be a function of epsilon when we get there. And I'll try to explain what that means in our example. And then finally, part 3 is to actually write the proof. So then write the proof. And the way you write the proof is by going from the absolute value of x minus a is less than delta, because that's the given, to what we want, the goal, which I wrote above, which is the absolute value of f of x minus L is less than epsilon. So we tried to work previous to this to understand what all of this language means, but sometimes you also just need to see it in action. So these are the 3 steps. So let's see if we can apply these 3 steps. So here's an example. So let's say we want to prove that the limit as x tends to 3 of x squared minus 6x is equal to, I'm going to say minus 9. Okay, so we can evaluate this limit because this is a continuous function, x squared minus 6x. And if you plug in a 3, you get 9 minus 18, which is negative 9. So we can see that this is the value of the limit because we have shortcuts, but that's not a proof. So to prove, we need to use the formal definition of a limit. And so first we have to remember what that is. So here's the definition. We say that the limit as x tends to a of f of x is equal to L, if and only if, when if and only if for every epsilon greater than 0, there exists a delta greater than 0 such that when the absolute value, or I should say 0, is less than the absolute value of x minus a is less than delta, when that's true, then the absolute value of f of x minus L is less than epsilon. So that's the formal definition. So we have to use that and meet that definition to prove that the limit as x tends to 3 of x squared minus 6x is negative 9. So that's when we go through these 3 steps here. That's when we apply these 3 steps. So step 1 is to apply the problem specifics to the definition. So in the problem, we want the limit as x tends to 3 instead of x tends to a. So a is a 3. And the f of x function is x squared minus 6x. And then it's equal to L. The limiting value L is 9. Or I'm sorry, negative 9. So the specifics that we apply is that L is negative 9, the function is x squared minus 6x, and that a is a 3. And basically, to apply those specifics to the problem, we rewrite what the definition would say if this specific problem was what it was being applied to. So I'm going to rewrite this by saying that this part here will change so that the L is now negative 9, the f of x is x squared minus 6x, and that a is now a 3. So I'm going to rewrite that definition so that we can say that if we can show that for every epsilon greater than 0, there exists a delta greater than 0, such that, and then in the specifics of the definition, I put 0 is less than x minus 3 is less than delta. When that's the case, then the function x squared minus 6x minus the limit of negative 9 is less than epsilon. So we put those into the definition. So let me take off the definition the way it was and then rewrite it and apply the specifics of the problem. And let's see if we can see what that looks like. So we want to prove that the limit as x tends to 3 of x squared minus 6x is equal to negative 9. So that means to show that, we need to show that the definition holds. So we need to show that for any epsilon greater than 0, there exists a delta greater than 0 such that, and this part of the definition always stays the same. You'll basically be rewriting this every time until you've remembered it very clearly. Such that when the absolute value of 0 is less than the absolute value, let's clean this up. When 0 is less than the absolute value of x minus a, and a is 3, is less than delta, then the absolute value of f of x, which is x squared minus 6x, minus L, which is minus 9, is less than epsilon. So by rewriting the definition with the specifics of the problem plugged into the definition, we are writing what we need to prove to show that this limit is minus 9, to prove the limit is minus 9. We have to prove that for any epsilon greater than 0, there exists a delta greater than 0 such that when x minus 3 is less than delta, the function minus the limit is less than epsilon. So then we would do steps 2 and 3. That's the first step. Okay, so in step 2, we want to write the goal of the problem. So the idea is we know that x minus 3 will be less than some delta that we've chosen. And the goal then is from that to show that x squared minus 6x minus negative 9 will be less than epsilon. That's the goal of the problem. So basically, the heart of creating the proof is to start with the goal, the f of x minus L part, and work backward and solve for the delta part that we have control of, x minus 3. And so let me do that. So I'm going to try to keep our steps on the page above me here as we write this. So I've rewritten it, and I'm going to take out this part in the middle here. So then this is true. So this is our goal. So we start with our goal and try to work backward toward the part we have control over, which is the x minus 3. So from here, I'm going to put this up here. So I start with, so this is part 2, step 2. We have x squared minus 6x, and I'm going to change minus 9 to plus 9. So this is what we want to be able to establish, that this is less than epsilon. That's where we want to end up after I simplified a little bit with the minus minus. Well, in this case, this is a not too challenging example, because hopefully it'll make it easier to understand what's going on. I'm going to try to solve this inequality for x minus a, in this case, x minus 3. Well, as we can see here, this polynomial factors, because it's a perfect trinomial, into x minus 3 squared. So the goal for this limiting proof is to show that x minus 3 squared is less than epsilon, and we have control over x minus 3. So I solve this for x minus 3. I'm going to square root both sides. So then I get that, and when you square root x squared, here's a reminder from algebra, the square root of x squared is equal to the absolute value of x. So, if I square root x minus 3 squared, I actually get the absolute value of x minus 3, which is good because that's what we want. And I'm square rooting both sides, so that has to be less than the square root of epsilon. So what does this mean? This means that if the absolute value of x minus 3 is less than the square root of epsilon, then working the logic back up, that means that x squared minus 6x plus 9 will be less than epsilon, which is what we need to make our proof. And so what we do is we then let our choice of delta be equal to the square root of epsilon. And that's part 2. We set the answer to be delta, which will be a function of epsilon, meaning delta will be equal to some expression involving epsilon, in this case, the square root of epsilon. Could have been epsilon plus 2 or times 5. In this case, it was the square root of epsilon. It'll be some function of epsilon. So you tell me epsilon, like maybe epsilon is 10,000. Then the way I choose my delta, in this case, is I take the square root of 10,000 and I get 100, and then I let delta be equal to 100. So this is a formula that tells me if you give me epsilon, then I can figure out delta. Now I need to show that when delta is set equal to this square root of epsilon, that I can then write the proof, that I can then establish that the square root of x squared minus 6x minus negative 9 is less than epsilon. But then part 3, which comes next, is basically what we just did in part 2, written backwards. So in part 2, we figured out what delta was, but then to write the proof, you're just basically going to take this and go backwards. You already have the steps already here, already written out for you. So let me try to then do the proof for you. So next is the final step, which is to write the proof. And the truth is you could do steps 1 and 2 on scratch paper, and then if you were writing up a formal proof, you would only write out part 3, the part that I'm going to write next. Parts 1 and 2 is how you figure out how to make the proof, and then in part 3, you actually write the proof. So here is what that will look like. All right. I'm going to actually erase 1 and 2 up above so I can leave what we did for part 2 below, so you can reference that while I write the proof. Okay. So here's what the proof would then look like. So to prove that the limit as x tends to 3 of x squared minus 6x equals minus 9, I need to prove that given any epsilon greater than 0, there exists some delta greater than 0. And in this case, I'm going to choose that delta to be square root of epsilon. And such that whenever x minus 3 on absolute value is less than delta, then the function minus L is less than epsilon. So here's what that looks like. Here's the proof. Given any epsilon greater than 0, could be 1/10,000th, could be 10,000, and we expect it to be a small number, but it could be anything. I'm going to then let delta be equal to the square root of that number, the square root of epsilon. So if I do that, then when the absolute value of x minus 3 is less than delta, and that's what we have to start with the proof, that whenever that's true, I then have to show that the function minus L is less than epsilon. So when the absolute value of x minus 3 is less than delta, then I know, let's give myself a little bit more space. I'm writing this proof. Then I know, because I chose delta to be square root of epsilon, right there it says let delta be square root of epsilon, that means that the absolute value of x minus 3 is less than the square root of epsilon, because that's what I chose delta to be. Well, now I basically go backward, part 2 that I had below here, from proof I go from bottom to top. So then how did we get to there? Then you can square both sides, and that will tell you then that x minus 3 squared will be less than epsilon. And we know these are both positive, but we can also then put absolute value on here at no expense. And then that means that the absolute value of x squared minus 6x plus 9 is less than epsilon. And then the last step is to then write that means that x squared minus 6x minus negative 9 is less than epsilon. And that's the proof. So the proof is really just this part right here. Because what we had to do, as we wrote in part 1, is you have to show that given any epsilon, there exists a delta, such that when absolute value of x minus 3 is less than delta, then the absolute value of x squared minus 6x minus 9, I forgot one more absolute value there, is less than epsilon. And this is the proof that shows that that's the case, because the delta that exists is the square root of epsilon. By choosing delta to be the square root of epsilon, then no matter what epsilon you give me, whenever x minus 3 is less than delta, the difference between the function and minus 9 will be less than epsilon. So there's something you can write at the end of a proof. There are 3 little letters, Q, E, D. That's Latin for quo erat demonstrata. It's the Latin, and that means that's what I was supposed to prove. That's how you say I'm done with my proof. So that's what a full proof looks like, and I hopefully was able to illustrate that there were 3 steps that I used to make this proof. Step 1 was to apply the specifics of the problem, what the a value, the function, and the L value are, rewrite the definition using those specifics so that you know what you have to show. Then in step 2, go from the goal of the problem, which is that f of x minus L is less than epsilon, and then from that, try to solve for the x minus a part. In this case, we took x squared minus 6x plus 9 is less than epsilon and solved it for x minus 3. And then whatever you get with epsilon on the other side will be some function in epsilon. That's what you set delta to be. And also, you've set up the logical steps that you need to work backward in the proof. So then you write the proof, given any epsilon greater than 0, let delta be equal to your function, in this case square root of epsilon, and then write the steps that you had in part 2 backward, so that whenever x minus 3 is less than delta, you can replace delta with what you let it be equal to, follow your steps backward, and you'll end up with the conclusion that the difference between the function and the limiting value is less than epsilon as desired. I know that's tough. Hopefully this helps, and reach out to me if you have any questions. Keep up the hard work. Good luck, everybody.